Okay, all right. So let's start by looking at the homework from yesterday. You had two basic counting principle problems. So the first one, a combination lock will open when the right choice of 5 numbers is selected, right? So, your lockers at school, combination lock, you got to turn it, right? But for this one, instead of 3 numbers, you have 5 numbers. If you have the digits 1 to 25 on the face of the lock, and you can use the same number more than once, how many different lock combinations are possible? All right, so like yesterday, you could kind of we have 5 possible entries, right? Each one of our lock combinations. So for each one of these, all right, we have the values 1 to 25, right? So including 1 and 25, okay, we have 25 possible entries. All right, so for this first number in our combination, we have 25 entries. Now, I told you that we're allowed to use the same number twice, right? So if our first number was 12, then your second number is allowed to be 12. All of the numbers could be 12, okay? So for the second option, we still have 25. For the third, we have 25. For the fourth, we have 25. And for the fifth, we have 25. And what we learned yesterday was we multiply all those together. Or in our case, we can rewrite it as 25 to the 5th power. And that should get us a fairly large number. $9,765,625.
I found that number fairly big, so I just multiplied 25 times 5.
Okay, so yeah, be careful there because 25 times 5 would be if we added all these 25s together, right? But we need to multiply. And okay, so that's a good point, right? This is a really large number, something that we haven't looked at. We are going to get very large numbers. We're going to see some interesting things. And actually, one of my favorite kind of math tidbits we're going to see, right? So yes, the answer is a very large number, 9,765,625. Right, so that's why these combination locks are great. Even a normal combination lock, I think, is from 0 to 40, and there are 3 entries, right? So that's 41 numbers. 41 to the 3rd power gets 68,921. So for your normal combination that you guys have, on your lockers in school, there are almost 70,000 different combinations, right? Different outcomes, which it would take a while if you had to guess all of them. You figure each combination would take a minute or two to try out. Well, that's 70,000 minutes of trying, which is a long time. All right, for our second one, you're registering a new boat. Boat registration numbers consist of a capital letter followed by 5 numerical digits. How many different combinations of boat registrations are there? So this we're combining, right? So boat registration is made up of 6 digits, right? The first one is a capital letter. And then the rest are the numbers 0 through 9. So we got to figure out, well, first, how many capital letters we have. Well, there are 26 letters in the alphabet. And then for each one of the numerical entries, right, we have 10 options for each of those. So we multiply all those together, and we'll have, 2,600,000. I can't. 2.6 million different boat registration numbers. All right. Any questions about that? And yes, again, we're going to end up with some very large numbers. And this is, this is pretty much, this is how license plates work, right? For a license plate, you even have a greater number, right? So real quick, just to talk about it before we get to the next part. Okay, license plate. License plate has 6 entries, but for each entry, you could enter either a number or a letter. So with the 26 letters and the 10 different numbers, we have 36 options to plug in to every every value has 36 options. So 36 to the 6th is, I don't even know, 1, 2, 3, 2 billion. So 2,176,782,336. All right. So even if we didn't, categorize license plates by states, if we just gave every car in the United States a license plate using the alphabet and the 10 numbers, 2,176,000,000 different license plates. Right. So the population of the United States is only 330 million. So there's probably enough license plates to go around. Okay. So we're going to continue with the counting principle. But now we're going to cover something new, which is kind of what we've been doing, but it's called permutations. So what is a permutation? A permutation of n different elements is an ordering of elements such that one element is first, one is second, one is third, and so on. So permutation is kind of like what we've been doing, but now the order of how we organize things matters, right? So there's a distinct first spot, and then the other spots follow. Now, usually, when we're dealing with permutations, we are not replacing. Okay, so remember yesterday, the first example we saw, we went through 2 different scenarios. The one where we replace the numbered cards back into the box or into the hat that we were picking them from, and the other where we didn't replace it. All right, so most of the time, not all the time, but most of the time, permutations are non-replacing. Once something is in the first spot, it can no longer be in the second or third or fourth or fifth or however many spots there are. Okay, so that's something that we have to take into consideration. So a very basic example is how many permutations of the letters A, B, C, D, E, F. All right, so how many different ways can we arrange those 6 letters? All right, so again, right, that's a long way of doing it. I can write out every different, right? So I have A, B, C, D, E, F, and then maybe I swap the E and the F, A, B, C, D, F, E, and then that would go on forever. And then I'd have B in the front, and then I'd have C in the front, and I'd go through all the different ways to have the combinations. But that's too much. So we're going to think about it like we did yesterday, right? So there are 6 open spots. All right, and we're trying to fill in the blanks. So for the first one, Okay, for the first spot, I have my choice of all 6 letters. 1, 2, 3, 4, 5, 6. Right? So I have 6 choices. Now, after I pick that first letter, whatever letter it may be, for the second one, we no longer have 6 choices. Now we only have 5 choices. All right, so if I picked A first, I can't pick A again. So I only have 5. After my second one, I've already picked 2 of my elements. So for the third one, I only have 4 left. For the fourth, I've picked 3, so 3 minus 6 is 3. And then for the fifth, I have 2. And for the sixth, I have 1. So if you notice, this looks like something we talked about last week. And that would be 6 factorial, which in our case would be 720. So there are 720 different permutations of the first 6 letters of the alphabet. All right, and if I tried to write them all out, we'd be here for a while. That would take today and tomorrow. Okay, so that actually leads us to one of our rules. Okay, as long as we're doing basic permutations, so the general rule is the number of permutations of n elements is n factorial. Okay, another way to think of it is there are n different ways, n factorial different ways of ordering n elements. All right, so as long as nothing else fancy is going on, it's very straightforward. If I want to find how many different arrangements there are of 10 books, well, that would be 10 factorial, which is, I forget, I should probably know that off the top of my head. No, 3,628,800. So there are over 3 million different ways to order 10 books. Think about that. That's crazy. Right? So you have a bookshelf, 10 books. You could be there for a lifetime trying to find all the different ways to organize those 10 books. Which brings me to one of my bits of really cool information. Let me get this. This number here, this ridiculously large number. I don't even know if I wanted to. If I wanted to put commas, I don't even know where to begin. Just to make it a little more organized, even though I don't know if this is helping much. This number here is a really interesting number. This is the number of ways to organize one single deck of cards. Right? So if you think about it, a deck of cards has 52 cards. So this number is equal to 52 factorial. If you punch that into a normal calculator, like this one, it wouldn't even know what to do. Right? Another way to look at this is in scientific notation. Let me make sure I got it right. In scientific notation, 8.06 times 10 to the 67th power. There are 67 distinct digits in this number. And again, this is the number of ways to organize a deck of cards. So theoretically, anytime that you shuffle a deck of cards, anytime you take any deck of cards and you just do whatever with them, more than likely, statistically, that shuffle, that arrangement of cards has never been seen in the world before. This number is beyond astronomical. Let me get some comparisons here for you. The distance from the sun to the earth. In the physics world is called 1 astronomical unit. It's a large way to measure things in space, okay? Instead of using miles and kilometers and things like that, because in space things are very large. So the distance from the sun to the earth is 149 million kilometers, or about 1.5 times 10 to the 8th. This is 10 to the 67th. Another comparison. The Grand Canyon. 40 billion meters cubed. That's what they estimate the size of the Grand Canyon is. If we fill this with sand, if we filled the Grand Canyon with sand, that would be four times 10 to the 19th grains of sand would take to fill the Grand Canyon. That number is nowhere near as large as 8.06 times 10 to the 67. It's not even comparable. It's like comparing Jeff Bezos' bank account to my bank account. It's unfathomable. And that's something I think is really cool. Right? Something as simple as a deck of cards. What's up?
The comparison, you didn't even need to do it like that.
Yeah, something as simple as a deck of 52 different cards. And there's almost, I mean, as far as we're concerned, there's almost an infinite amount of ways to rearrange those cards. It would take more than a lifetime to find every single combination. Right? So playing poker and things like that, you know, a lot of that plays into the statistics of card games. Right? Every time you shuffle a deck of cards, that organization of cards has never before been seen. And that's something I think is really, really cool. And it's, it really boggles the mind to think of a number that large, because we can't. Okay. Even the sun. Let's see. Let me look
Mr.
up.
Murray,
What's up?
does this like play a part in when people like count cards and like gambles? I don't know what that's like.
Not so much. That's a little different. Maybe at the end of the year we could get into that. I can talk to you about that. Well, we are going to get into probability, which is what counting cards is. So we'll talk about it a little bit. We'll talk about cards a lot. The sun, the volume of the sun is 1.4 times 10 to the 1, 2, 3. 18. 1.4 times 10 to the 18. Okay. The volume of the sun is 1.4 times 10 to the 18th cubic kilometers. And scientists say that you can probably fit about 1.3 million Earths inside the sun. And again, that number is nowhere near this. To have 67 zeros follow something is, it's hard to wrap your mind around. So I apologize for the slight, off track. I mean, it is what we're learning, but yeah, we'll pick up with some more of this tomorrow. All right, so it's just something to think about. All right, and a lot of people get into things like number theory and, different probabilities just from, thinking about stuff like this. This is, it's out there. All right, guys. So we'll pick up with some more permutation stuff tomorrow. And yeah, have a good day, guys. I'll see you later.
Bye, too.